Is asking for the feedback transconductance amplifier of figure P11.56. Derive expressions for A beta, AF, RO, and ROF. Evaluate AF, ROF for the case of GM1, GM2 is equal to 4 milliampere per voltage, RD is equal to 20K, RO2 is equal to 20K, RF is equal to 100 ohm resistance, RL is equal to 1 k ohm resistance, and for simplicity, neglect RO1 and take RO2 into account only when calculating output resistances. Okay, so here the question is asking to find out the expression for A beta, AF, RO, and ROF, and also finally we have to find out the answer, the real value of AF and ROF using these parameters. Okay, now let's see how to do this. So this is the circuit diagram provided to us. Here we have a NMOS connected with a PMOS, and we have resistor and input voltage. It's better to draw the small signal equivalent model in order to do this problem. So let's go and draw the small signal equivalent model. So first, in the small signal equivalent model, we know that it comes like GDS. So ground here, and then drain here, and then source in the bottom. So this is the small signal equivalent model. First, if we take care of this NMOS transistor has a input voltage Vi. So let's put that one right here. So here, this one Vi right here, and whatever the voltage we connect to the virtual ground. So this is Vi connected to the ground right here, and the voltage between the gate to source we call VGS, and between drain and drain to source there's a current flow. And in small signal equivalent model we express the current flow in a current source, and that will be expressed with transconductance multiplied by whatever the voltage right here. In this case this is VGS, so GM1 VGS. And after that, if you look at the drain has a resistance of RD, so that one will be right here, and that will be connected to a virtual ground. And after that, now we are going for the PMOS. Now the PMOS, what's the difference between NMOS and PMOS? In the PMOS, instead of VGS, we are going to have VSG. Okay, and that is it for here. And then there's a current flow. The current flow for the PMOS is going to be opposite direction of NMOS, so it's going to be going upward. And the transconductance, let's call it GM2, and whatever the voltage there, that's VSG, so GM2 VSG right here. And if you look at the PMOS, that has two resistors connected in series, and that is from drain to source. So here we can draw them like this and connected to virtual ground. So this is the load resistor right here, and this one is the feedback resistor RF. Okay, so this is the circuit, and also the current flow I note is right here, and this is our small signal equivalent model. Now we can go ahead and find out each expression. First, if you are looking at A is nothing but output current over input voltage, so there is A is equal to output current I0 divided by the input voltage Vi. And if you look at the output current, this is the exact same current flowing through this GM2 VSG is the exact current flowing through the this. So this I0 is equal to exact this current. So that is, we can say that I0 is equal to GM2 VSG. Okay, let's call this an equation number 1. Now this VSG is nothing but, if you expand VSG, that is nothing but Vs minus Vg. And if you look at the source is connected to the ground, so Vs we know that is to be 0, and the gate voltage of the first one, if you notice here, voltage is nothing but I times L, Ohm's law. We can use the Ohm's law right here. So when we are saying VSG, we are looking at the MOSFET gate right here. Ohm's law says, if you look at the small signal equivalent model, that looks better. So Ohm's law says the currents times V is equal to I times R. So the current flow through that one, the first, okay, if you consider the second MOSFET, the current flow through this one is the whatever the current from here, that is GM1 VGS1 times the RD resistance, should be the voltage right here. Okay, GM2 VGS1 times the RD should be, and that should be negative because it's opposite direction of the NMOS. So this is going to be negative GM VGS times the RD. Okay, and negative negative turn into positive, so this is GM1, so this is become GM1 VGS times the RD. Now we have the expression for the VSG, and if we combine this VS, if we rewrite the I naught equation, I naught is GM2 times VSG, and for VSG now we have this expression. Okay, so we have to multiply this GM2 with this expression. Let's do it in the next page. So VSG is equal to no, I naught. Let's bring the I naught. Equation number 1, I naught is equal to, let's rewrite the equation, GM2 times VSG and GM2 times the VSG expression is GM1 VGS RD, GM1 VGS times the RD. Okay, this is I naught expression. Okay, but before I express I naught, VGS RD, before I express I naught, or let's say this is equation number 2, but here we can do one more thing, that we can also find the expression for the VGS as well by applying KVL at this loop right here. KVL says that addition of all the voltage is equal to 0. So if we apply KVL in this loop right here, if you consider a small signal equivalent model, we are applying the KVL over here. So if you look at the voltages over there, KVL at let's say KVL, so this is negative VI right here, plus VGS plus the current times the resistance. VI plus VGS plus GM1 VGS times RF should be equal to 0. Okay, therefore we can also say that therefore VGS is not VGS. If we take VGS common here, that will become 1 plus this GM1. We already take the VGS outside, so this is going to be GM1 times RF, and if I take the VI to the other side of the equation, that's going to be a positive VI. Now if we write the expression for the VGS right here, VGS is nothing but this VI divided by 1 plus GM1 times RF. Now we have the expression for the VGS. Now we can plug it in this equation and express it in a better way. So we can say that I naught is nothing but in the equation number 2 we derive that I naught is gm2 gm1 gm2 vgsrd gm1 gm2 vgsrd and gm1 gm2 instead of vgs we can express this one vi over 1 plus gm1 rf vi over 1 plus gm1 rf and that one multiplied by rd. This is I naught, but we are doing all this to express a is nothing but I naught divided by vi. A is I naught divided by vi, and if you look at this expression we have vi on top of the I naught expression and that one divided by vi, so vi cancel and we will end up having this way a to be gm1 gm2 divided by 1 plus gm1 rf times the rd, and that is the expression for the a. Okay, the next one is they are asking the expression for the beta. When they ask for the beta expression we have to consider the feedback resistance and feedback voltage and the current flow. So if you look at the circuit, the feedback resistance right here RF, and then feedback voltage VF right here, and the current flow through this is I naught. If I just take that part alone, the circuit is going to look like this. We are going to have the feedback resistance right here, that is RF. Across that we have the VF voltage right here, and then there's a current flow I naught right there. Okay, and from this one we can say that beta is nothing but this feedback voltage divided by the I naught current, and if we express this VF in terms of ohms, so V is equal to I times R, the current flow through that is I naught, and then the resistance is feedback resistance which is RF divided by I naught. Here I naught cancels, so beta is equal to RF. Okay, so this is beta, and that is the second part of this question. And the next one is A beta. A beta is nothing but the A we derived, which is this one gm1 gm2 1 plus gm1 rf times rd, gm1 gm2 divided by 1 plus gm1 times rf times rd, gm1 times rf times rd, and that one multiplied by beta. Beta is rf, so this one multiplied by rf is the A beta. Okay, let's round the answers first. So beta is this, A beta is this, and then A is this. Okay, and the next one is we have to find out AF. The AF AF have an expression. The equation for the AF is equal to A over 1 plus A beta, and we have expression for both of them. A expression is right here, gm1 gm2 over 1 plus gm1 rf times rd, gm1 gm2 over 1 plus gm1 rf times rd, and then that one divided by 1 plus A beta is this expression, gm1 gm2 over 1 plus gm1 rf times rd times rf. So gm1 gm2 over 1 plus gm1 rf times rd times rd times rf. Okay, and this is our AF. Okay, here we can try to simplify some of the terms. Okay, you can simplify this one in a simpler form. If you simplify, this one comes out to be gm2 gm1 times rd divided by 1 plus gm1 times rf times 1 plus gm2 times rd. This is the simpler expression. Okay, so this is AF. The next one is RO. RO, the output resistance. Okay, so when we are considering the RO output resistance, what we have to do is we had to open circuit the load resistance. So if we look at here, if we open circuit the load resistance and draw the small signal equivalent diagram, it's going to look like this. Here we are going to have the current source, GM1, actually GM2 VD1. Okay, and here we will have the we're just looking at the PMOS. Okay, so there will be the RO2 output resistance, and that is parallel with the feedback resistance, which is RF. We are looking at right here, we open circuit the RL, so RL is gone, RF is there, there's output resistance RO2, that is only visible when we draw the small signal equivalent model, so that will be there. And then we also connect this one with a 1 voltage. Okay, let's put plus minus here, 1 voltage, and there's a current flow I notice here. Okay, maybe it's better to point like this. Okay, so this is the small signal equivalent model, and from this one, if you look at I0, this I0 is nothing but this 1 voltage divided by this parallel resistance, which is RF parallel to RO2. And if you rearrange this equation, we can say that 1 voltage over I0 equal to RF parallel RO2, and this 1 voltage over I0 is nothing but that's the output resistance. Output resistance, therefore RF parallel RO2. The straightforward method is you look at the circuit, you open circuit the RL, and you know the RO2, and RO2 is parallel with RF, and that is the straightforward method, but this is the analogy. Okay, so now we have the output resistance, and finally we have to express ROF. This ROF is nothing but, let's put the RO is this, and RF parallel RO2 is nothing but product over sum RF times RO2 over RF plus RO2. That will be the expression. And then ROF is nothing but this output resistance multiplied by 1 plus A times beta, and output resistance expression is nothing but RF parallel RO2, and that one multiplies by 1 plus A times beta, and A times beta also we have expression for it, so we can bring that one over here as well. A times beta has an expression of this right here, gm1 gm2 over 1 plus gm1 RF times RD times RF. So gm1 gm2 over 1 plus, okay, wait a minute, 1 plus gm1 RF RD times RF, 1 plus gm1 times RF times RD times RF. Okay, this is gm2 right here. Okay, this is the expression for the ROF. And finally, so we did all of them. We found out A expression for the A beta, AF, RO, and ROF. Okay, so that is the first part of the question. and then they are asking evaluate AF and ROF for the case for these parameters. So they're asking us to find out AF and ROF values, and we have to use these parameters. If you look at the expression for the AF, here we have the simplified formula for the AF, which is gm2 gm1 rd over 1 plus gm1 rf times 1 plus gm2 times rd. So let's bring this one again here. Let's put in a different color. So we know that AF is equal to gm2 gm1 times rd, gm2 gm1 times rd divided by 1 plus gm1 rf, 1 plus gm1 rf, and that one multiplied by 1 plus gm2 rd, 1 plus gm2 times rd. Now all the values are readily available. We know the transconductance 4 milli, gm1 gm2 both of them are 4 milli. So here this is 4 milli times 4 milli, and then rd resistance is also provided to us, that is 20k. So 20k right here, and then divided by 1 plus 4 milli again, multiplied by the feedback resistance, which is 100 ohm resistance. So 100 right here times 1 plus gm2 4 milli, rd is 20k. And if you calculate the value, you're going to end up having that to be 9.3 milliampere per voltage. So that is the AF value, and then next they are asking for the ROF value. For ROF, we had to use this expression, which is RF parallel RO2 1 plus gm1 gm2 ROF. Let me copy this and paste it in the next page. Okay, so this is the equation we are going to use, and in this one RF is nothing but 100 ohm resistance, and then RO2 is also provided to us, which is 20k. So this is 100 parallel 20k times 1 plus gm1 gm2, which is 4 milli times 4 milli, that one divided by 1 plus gm1, that is 4 milli, that one multiplied by the feedback resistance, which is 100, that one multiplied by the rd, I think that's 20k. Yeah, 20k times 100. Okay, solve for this one. You will end up getting the value to be 11.471 kilo ohm resistance, and that's our ROF value. And that's it for this video. I hope you guys found this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my